Welcome to the third video on conic sections. Here we'll discuss the parabola. Before entering this video any further, you're going to need the skill of completing the square. I have a separate video on that in my YouTube channel, Recital Math. Assuming that you're comfortable with completing the square, let's go on to look at the parabola. In general, the equation you see in the corner could be any conic section, where A, B, C, D, and E are numbers. Now, in particular, if either A is zero or B is 0, then you're likely to have a parabola. Do you see the spelling of the word OR there? It's actually XOR. That stands for an exclusive OR. That means that we're likely to have a parabola if A is 0 or if B is 0, but not both. That's the meaning of exclusive OR. After all, if A and B were both 0, wouldn't our equation just be that of a straight line? You may or may not recognize graphing of a straight line, but so we're going to consider in this video problems where either A is 0 or B is 0, but certainly not both. Those are not of interest to us at this point. Now, if you look at the two formats of the equations on the right here that just appeared, those are the formats that if a parabola has an equation in, that you're likely to get some meaningful information about the parabola. And so we're going to start this video, before we get to our main problems, looking at equations that are in this particular format first, which is not the standard form of the conic section, but it is nonetheless something worth looking at. And I want to share some mathematical discoveries with you. First of all, you can see the example on the left is in this particular format here. And so let's take a look at what mathematicians have discovered about the graphs of equations that are in this format. One major discovery mathematicians have made is that if you take the two numbers shown in green and red here, the +2 and the +3, and you take the opposite sign of each, which in this case is -3 and -2, that you will get the vertex of the parabola. The vertex of the parabola is the turning point. So what that tells me, just from the equation being in this format, is that I have a vertex of -3, -2. Here's another discovery mathematicians have made. It's sort of a two-part discovery. If you have an x-squared parabola, and I call this an x-squared parabola because there's no y-squared in it. This would be the kind of problem, for example, look at the upper right corner. This formatted equation here might have come from one in which B is 0, meaning effectively that there's no y-squared term. Mathematicians have discovered that if you have what I call an x-squared parabola, that if the number in front of the completed square is a positive number, then you're going to have an upward facing or concave up parabola. Whereas if the number in front of the completed square is negative, you're going to have a downward facing or concave down parabola. Now the number itself, besides just whether it's positive or negative, has an impact on the width of the parabola, and we'll discuss that at the very end of the video. But for now, suffice it to say that you can tell by this number whether it's positive or negative as to whether the parabola will be opening upward or opening downward. Oh, side note, whenever there is a coefficient of 1, we often don't write the 1. So if you just see a floating negative sign there, think of it as a -1. Now let's take a look at a different parabola. This one is what I would call a y-squared parabola. This parabola has a y-squared term, but no x-squared term. Looking in the upper right corner, if we were to see this equation in standard form of a conic section, it would be the case that A is 0. A is 0 effectively meaning that there's no x-squared term. And we can see that this equation is in this format. Again, mathematicians have discovered that if you take the opposite sides of the numbers being added or subtracted from x and y, that you will have the vertex or turning point of your parabola. So just from the +1 and the -4 in the equation, we know, because of its format, specifically, that the vertex is going to be at -1, 4, which is right here. Furthermore, mathematicians have discovered that when the multiplier of the perfect square, or completed square, in this case +2, when that number is positive, and you have a y-squared parabola, that your parabola will be opening to the right. Now, the fact that the 2 is positive makes it open to the right. The 2 itself, or whatever that number might be, will have an effect on how wide or narrow the parabola is. We'll get into those details at the end of the video. But for now, suffice it to say, positive number in front of completed square, with a y-squared parabola, it will be opening to the right. And reversely, if the number in front of the completed y-squared is negative, then your parabola will be opening to the left. And again, the number 1/2 affects the width, as did the +2, but we'll get into the details of how that works later. Now, these two formats, as you see here on the right side of your screen, are incredibly valuable because we can find the vertex of the parabola and know its direction by just knowing that the equation is formatted that way. Unfortunately, the standard form of a conic section is often the form in which the equation is given. So for example, suppose we wanted to graph this parabola. Well, this parabola isn't in the preferred formats that you see on the right, and therefore we can't really tell anything about it mathematically. We can't read its vertex or even necessarily know the direction it's opening just from this information. Well, first of all, notice that it can't match this format because that second format there has an x squared in it. So my goal now is to get this parabola equation to be formatted in a way that I can read the vertex and direction of opening. So let's go about some algebra, and I'll show you how to get it into our preferred format. First thing I would do is put all my squared terms together, because if I can put in this case, the y is the variable being squared here. If I can put my y terms together, and that's my squared variable, I can factor out the lead coefficient of the y's. Why would I want to factor out the lead coefficient? You don't have to, there's other ways to do this. But I like to factor out the lead coefficient. Reason? If the lead coefficient is factored out, I can do the completing the squared process on what's in the parentheses only. And that's a monic, it's going to end up being a monic trinomial when I complete the square. And so I prefer to factor out the lead coefficient just to make the math a little easier. Now here's where completing the square comes in. Notice how I've completed the square here. You may see it in red. If this is not a familiar skill to you, you're going to want to either A, pause the video now and convince yourself that that is a completed square, or even go back and watch the video on completing the square. Either which way, we'll move on from this point. The purpose of completing the square is that, for me anyways, is I can now redistribute the 2 that I factored out. And if I redistribute that 2, notice what happens here. But the benefit of all this is that now I have a completed square on y, and I'm more in a position to get my equation into the preferred format. So what I did was I then combined the -18 and the +17. -18 plus 17 is -1. And then, to get into the preferred format, I subtracted the entire term on the left, brought it to the other side, and now you can see that I have algebraically massaged this equation into the format that I want. What was the whole purpose of this, you may be wondering? Well, the purpose of getting it into that format was to be able to discern some information quickly about what the graph would look like. And now that I have my equation in this format, I'm in a much better position to graph this parabola than I was in the beginning. So now, just by looking, I can see that the vertex is going to be 1, 3, and because the number in front of the completed square is negative, I'm going to have a leftward parabola, per the discoveries we discussed earlier. Now, the fact that there's a 2, not just a negative 2, but the fact that there's a number 2 there does have an impact on the width of the parabola. And it turns out the bigger the multiplier in front of the perfect square, the more narrow the parabola is going to be. Again, more details on the narrowness or wideness of the parabola later in the video. So let's take a look at one more example. This is clearly a parabola with an x squared, and so I'm going to complete the square here on this portion of the parabola. Again, if that's not a skill that you have, you might want to pause and figure that out. But now that I've completed the square here, I can combine the minus 16 and the positive 22. Minus 16 plus 22 is positive 6. Well, at this point, there are many things I could do. I opted to add 3y and subtract 6 from both sides, and then just reverse the equation so it would look more like the format that I prefer. Now, to get this into a preferred format, notice that there's a 3 coefficient in front of the y, but my preferred format didn't have a coefficient there. So I've opted to divide both sides by 3, and that gets my equation into the exact format through which I can tell some information about the parabola. And now that I've reformatted my equation, by the way, these are both the same equation, but now that I have it in a new format or style, I can immediately tell that because of the positive 4 and negative 2, that my vertex is going to be negative 4, positive 2, which is right here. And because of the nature of the fact that I have a positive number in front of my completed x squared, tells me that my parabola is going to be opening upward. Now again, how does the number itself, the 1/3, affect the width? We're getting closer to that, but suffice it to say for now that a positive multiplier will lead to an upward facing parabola if you have an x squared, the completed x squared. So let's summarize the discoveries that mathematicians have made about parabolas so far. In general, when we have an equation in this format, your standard conic section format, if either a is 0 or b is 0, but not both, then you will have a parabola. That parabola can then be converted into one of our two preferred formats, depending on if it's an x squared parabola or a y squared parabola. In other words, depending on if b is 0 or if a is 0. And once we're in that format, we can use the numbers being added or subtracted from or to the variables to determine the vertex. I'm going to just generically place a vertex in quadrant 1 here, just not because it necessarily has to be, just because I have to put a dot somewhere to give you a general idea. But of course, for the vertex to actually be in quadrant 1, both of those numbers in red and green would have to be negative. But again, the vertex could be anywhere, but that's one thing mathematicians have discovered. And furthermore, mathematicians have discovered if the number in front of the completed x squared is positive, then your parabola opens up. If the number in front of a completed x squared is negative, then your parabola opens down. If, by contrast, you have a y squared parabola, and the number in front of it is positive, then you're going to be opening to the right, whereas if the multiplier of the completed y squared is negative, your parabola will be opening left. And lastly, the issue I've been promising to get to is how wide exactly will your parabola be? Well, in general, the larger the multiplier, the more narrow your parabola will be. But let's get more specific and look at an example we already saw. But this time, let's try to not only graph it in the right direction, and I believe we saw that this was if I'm not mistaken, that this was an upward-facing parabola. Let's look a little bit more granularly about how wide exactly this parabola will be. So, one of the things we saw earlier in this video was all the messy algebra that converted the standard form on the top to the preferred form on the bottom. And once we found the preferred form, we knew the vertex was negative 2, 4. I'm sorry, negative 4, 2. And we knew that because the 1/3 was positive, that the parabola would be opening upward. Because whenever you have a positive multiplier in front of a completed x squared in this perfect preferred format, that's an indication that your parabola is facing upward. But we don't know if it's going to be narrow, not quite as narrow, a little wider, a lot wider, or super wide. We have no idea the exact width of this parabola. We simply know its turning point or vertex and its direction of opening. But which one of those parabolas, if any, would have been right? Well, depending on your professor or teacher, they may not care. If you're only studying parabolas for the purposes of getting points on a math test and getting things right and then moving on with your life, then there's a really high probability that your teacher just wants to see that the vertex is in the right place and that the parabola is opening in the right direction. But if we want a more precise graph, there's something we can do to help us determine the width, essentially, of the parabola, and how wide to draw it anyways. One thing I like to do is pick a number that's maybe 2 or 3 spaces away from the vertex. This vertex had an x-coordinate of negative 4, so I'm just going to pick something 3 spaces away in this case. And just pick an arbitrary number somewhat near the x-coordinate or y-coordinate of the vertex, depending on which the case may be, and plug that number into the original equation. Or, if you prefer, plug it into the new preferred format equation. They're both the same equation. But if you were to plug negative 1 into either of the original equations, you would find y. If you're the kind of student who likes to study every little number in a problem, go ahead and do that now. Hit pause. But primarily, it's not the algebra I'm interested in here. I'm interested in the concept that I picked an arbitrary number for x, and I found out what y would be in that case. And so I can now plug, now knowing that x is negative 1 and y is 5, I can now plot the point negative 1, 5 on my parabola. And now that I know that, I actually know a second point on this parabola. Because I know this parabola is opening upwards, and so it has to be symmetric about this line. That means it's also going to pass through this point. Now you could plot lots of points on this parabola, but ultimately you're going to get a sense of what the width would be just by plotting a few points. Now before you get too precise about it, let me point out the following. If you're going to really go crazy and try to get a very exact graph of this parabola, you're going to have to plot a lot more points than just those 3. And kind of defeats the purpose, because there are 2 ways to graph a parabola, with a calculator and without. If you're graphing one with a calculator, you're going to want to get a very precise image. But the whole point of this video is graphing them without a calculator. And if that's your goal, then having tons of precision doesn't really serve any purpose. So plot a few points, get an approximate location of your parabola, and don't worry about being super specific, because if we wanted something specific, we would be using a calculator, which we're not. And that completes this 3rd video in the series of 4. And thank you so much for watching.